whenever we want to quantify the relationship between the variable, whether we can compute the covariance or whether we can compute the correlation. So now what's the difference? So normally the covariance is basically indicating the direction of the linear relationship between the variables. Okay, so whether by increasing the one variable, the what's the effect on the other variable, whether it is also increasing or whether it is also decreasing. Okay, so depending upon by increasing one variable, what's the effect, or you can say what's the direction of the other variable. So in order to compute the covariance between the two variables, how we can do that? The formula is over here. So x is representing the first variable and x bar is the average of that variable. The second variable is y and this is the average of the second variable, where I and j is representing the different observations. So we multiply this one and then taking the average. So this is basically the covariance, which is just like a variance if we have only a single variable, because in a variance formula that is basically the variance of x, what we are doing is we are saying that xi minus x bar square over n. So which means we can repeat this two times, because in a covariance there are two variables. So which means we can say that the deviation of the first and the deviation from the mean of the observation of the second variable, we multiply those two components and sum them and taking the average, that would be called as a covariance. Okay, so when we are calculating the covariance, as we have say that it is basically calculating how the two variables are depending on each other. So higher the number, that is indicating the higher the dependency on each other. So the covariance answer can be ranged from minus infinity to positive infinity, and it is also a scale dependent. Okay, so depending upon what's the scale of x and y, so we can multiply those variables and then find out the scale of the covariance. Whereas if we want to check the relationship between the two variables, we can also calculate, instead of the covariance we can calculate the correlation, which is basically calculating the two components, direction as well as the strength. Okay, whereas covariance is only calculating the direction of the two variables. So it is calculating both the direction as well as strength between the two variables. And remember that when we are saying the correlation, which we will talk about, that is basically we are calculating the linear relationship between the two variables. Okay, not the non-linear one, we are calculating the linear one. So the advantage of the correlation is basically it is using the standardized value instead of the actual you can say variable. Actual variable mean it is not depending upon any particular unit. Okay, whereas covariance is not using the standardized value, so that's why the answer of the covariance is a unit dependent. So correlation is basically the standardized value, and how we can standardize the answer of the correlation by dividing the covariance answer with the standard deviation of variable first variable and with the standard deviation of the second variable. So the answer would be called as a correlation. So as we have discussed earlier, so the correlation is basically calculating the strength between the two variables. Okay, and the answer would be in comparison to the covariance, so which is basically lying between minus infinity to positive infinity. The correlation and answer, due to the standardization, it is always lying between -1 to +1. So we can say that if the answer of the correlation coefficient is -1, basically this negative sign is indicating the direction. The value of 1 is basically indicating the strength of the variables between two variables. So -1 mean they have the perfect negative relationship. So you can say that by increasing the one variable, all the others, all the values of the other variables is also decreasing. Okay, so by increasing one variable, the other variable's value is decreasing. Okay, or you can say the 100% values of the one variable, if it is decreasing, the other variable's value is increasing. So they have the inverse relationship. If it is, the answer is +1, so again positive is indicating the direction and 1 is indicating the strength, so they have the direct relationship, or you can say a positive relationship. So they have the unidirection. If one variable is 100% increasing, the other variable values are also 100% increasing. Whereas if the one value is 100% decreasing, the other values is also decreasing. If the value is 0, so that means there is no relationship between the two variables. So that means if the answer is like minus 0.6, so that is indicating the 60% values of one variable. If it is increasing, the other variable's value is decreasing, right? So similarly, the positive zero point 0.4 mean the 40% of the variable, one variable is increasing, the other is also increasing, or you can say that the 40% values of one variable is decreasing, the other variable is also decreasing. So they have the unidirection, right? So this is the main difference between the covariance and the correlation. I hope you got the idea regarding the covariance and the correlation, because correlation is using the standardized value, so they are not the unit focus. Okay, so they will provide us in the answer between -1 to +1, okay, which is unitless. Okay, that is indicating the strength between the two variables as well as the direction between the two variables. If we move towards more than two variables, so then we can develop a variance covariance matrix. So this is basically a variance covariance matrix. Okay, so in variance covariance matrix, actually the diagonal values are the variances of the variable. So you can say that if this is x0 variable, this is x1 variable, this is x2 variable, so this is x0, this is x1, this is x2. So this value is basically indicating the variance of x naught variable. This is indicating the variance of x1 variable. This is a variance of x2 variable. Whereas sigma square 0, 1 is indicating the covariance between x naught variable and x1 variable. Okay, so similarly we can represent the correlation matrix. Okay, so the correlation matrix can be represented with, okay, that is 0 0. Okay, or you can say normally this would be 1. Okay, so this would also be 1, this would also be 1. Okay, over here in a correlation matrix, so this would be 1, this would be 1, this would be 1, and this would be written as 0 1 0 2. So that is the correlation between x0 variable and x1 variable, x0 and x2. Okay, similarly x1 and x2 variables. Okay, so you can develop the correlation matrix as well as the various covariance matrix if you have the multiple variables. Okay, now let's calculate the variance covariance values between the two variables in which we are interested to find out the relationship as well as the correlation. So for that I'm using a data which is the exam anxiety data. So where we have the code, which is basically you can say represent the independent participant score, the first participant score, the second participant score, and this is basically indicating how many time he has revised. Okay, mean the total hours he spent in time to revise the syllabus. Okay, that is basically in hours, whereas exam is indicating the exam percentage score, or you can say exam performance, whereas anxiety is basically there in anxiety questionnaire answer is, that is if there is a 80% anxiety, what's the exam performance and so on, and we also have the gender. And now we want to find out the correlation as well as the covariance between the exam performance and the anxiety. So let's do that with Excel first, and then later we will discuss in the R. Okay, so how we can do that in Excel? So first of all, I'm calculating manually, means with the help of Excel, and then we will also use the formula of the Excel in order to calculate the correlation. Okay, so for from this data set, which is basically the exam anxiety data, which is basically 103 participants data. Okay, so I have picked only the exam variable and then anxiety variable. Okay, so for that, first of all, if I want to calculate the covariance, so the formula of the covariance is x minus x bar. So for that I need to calculate the average of exam performance as well as the anxiety. So for that I have calculated the average. of this, that is basically the average formula from the Excel, and we have selected all these values. Okay, so this is basically the average of an anxiety, as well as we have used the standard deviation formula. So either you can use the population standard deviation of the sample like STD. So you can use population of the sample. So right now I'm using a population standard deviation, and the range of the data is the same. So this is basically the standard deviation of the exam anxiety. Similarly, we can find out the exam performance. Sorry. So the exam anxiety perspective, if we say that the average is this one and this is the standard deviation. So now in order to calculate the covariance, first of all, we need to calculate the first component, that is each value minus x bar. So for that I have calculated dx. Okay, and how we can do that? This value 40 minus average of this one. So we have done this by freezing the value of b 105. Okay, once we have applied this particular formula, so we can drag and drop, okay, till over here, right? So this is basically the x minus x bar. Similarly, we can calculate y minus y bar. So this is the value of y minus the average of this one. Okay, and we can calculate the y minus y bar, right? If I drag and drop till over here. Now, in order to find out the covariance, this is x minus x bar, this is y minus y bar. So we need to multiply this one. So that's why we have multiplied these two columns. Okay, once we have done, again we can drag and drop. And then if I find the average of this particular column, okay, if I find the average of this particular column, which is over here, so this is basically a covariance. Okay, that is the formula of the covariance, which is indicating that exam anxiety as well as anxiety as well as exam performance have the inverse relationship. So we can say that as the anxiety level increases, so the exam performance decreases. Now let's find out the correlation. So how we can do that? The formula for that is covariance, okay, divided by the standard deviation of x divided by the standard deviation of y. So covariance we have calculated over here, which is f05 divided by standard deviation of x and standard deviation of y. So this is basically the correlation coefficient, right? So this is how we can manually calculate it. Similarly, you can also calculate using Excel. The formula for that is basically the correlation, okay, correl, and we have to pick the first range of the data, okay, that is basically x, and then y range of the data, okay, that is this one. So this is correlation. So you can see that they have the same answer. So how we can interpret this one? So we can say that 44% of the time when the anxiety level increases, the exam performance decreases. Okay, so this is how you can find out the correlation using Excel. So now let's discuss a bit more about the correlation perspective. So as we have already discussed, basically the correlation is basically quantify the strength between the two variables, okay, and the relationship basically that is must be the linear relationship it would be able to quantify. If the two variables do not have the linear relationship, or you can say the straight line, okay, then it wouldn't be able to calculate the correlation which we are applying. That is basically right now in Excel we have applied the Pearson correlation. So what is that? We will discuss later as well. So the formula we have applied, which is basically the Pearson correlation coefficient. So in order to apply the Pearson correlation coefficient, which is basically quantify the strength of the linear relationship between the two quantitative variables, okay, that means that must be the continuous variables, okay, then we can find out the correlation. So in order to apply the Pearson correlation coefficient, we have some assumptions we will discuss later, but I hope you have cleared that we can calculate the correlation coefficient, which is the Pearson correlation coefficient, if you are interested to find out the strength of the linear relationship between the two continuous variables. Okay. So you can also graphically represent the relationship between the two variables with the help of the scatter plot, which is on x-axis there is a one variable, on a y-axis, and these dotted lines are basically representing, each dot is representing the value of x1 against the value of x2. Similarly, this dot line is indicating the value of x and against that the value of x2. So if these dotted line are, as you can see over here, basically this is indicating as the value of x1 increases, the value of x2 is also increasing. So they have the relationship, or you can say the positive relationship. So if we calculate the correlation coefficient from this data point, they said this is the 0.9. So we can say that 90% of the time when x1 increases, x2 is also increases. Over here we have the weak relationship, which is 0.1. Okay, so only 10% of the time when x increases, x2 is also increasing, or it is near to the zero, we can say that it might be possible they have not a significant relationship between the two variables. Okay, over here we have the negative relationship. So as we have seen that if the correlation coefficient, mean the answer of the correlation, which can be represented with r, the answer of the r is always lying between -1 to +1, as we have already discussed. If the answer is exactly positive, so this would be called as a strong positive relationship. If 0, then we will say there is a no relationship or a very little relationship. Okay, near to 0 if it is. Okay, exactly 0, that means there is no relationship. -1 means there is a strong negative relationship. So this is how we can descriptively quantify the value of the r, which is basically the correlation coefficient. So in order to test it, okay, whether this correlation coefficient between the two variables is significant or not, we need to apply the testing of hypothesis. For that, our h naught is that there is no correlation between the two variables, or we can write down technically the rho is equal to 0, okay, which means there is no correlation between the two variables, or alternative there is a relationship, or there is a correlation between the two variables. So this is two sample t-test. Okay, this is two-sided two-tailed t-test. Okay, two-tailed test. Whereas it could be possible that we can say that rho is less than or equal to 0, or alternative is greater than 0. Okay, so or we can say that h naught, the rho is greater than or equal to 0, or alternative is rho is less than 0. So these two is called as one tail test. Okay, so depending upon how you want to test whether there is a relationship with respect to only the two tails, so that means it is equal to 0 or it is not equal to 0. It could be less than 0 or greater than 0, but there is, we also see the direction whether it is a negative or the positive. Okay, so this thing we will perform in R later. So, but before discussing what kind of the correlation techniques we have, first of all, let's discuss, because most of the time we are confusing with the causation concept as well as the correlation. So when we are saying we are interested to find out the correlation between the variable, that means we want to check whether the two variables are relating with each other or not. Okay, but that doesn't mean the action A or the variable A is causing to increase B or decreasing B. Okay, if this is the case, if one is causing to increase, decrease, or increase, then there is a causation concept, that is a cause and effect relationship. Okay, like if we say that if action A is causing to outcome the B, or you can say increasing the B or decreasing the B. So here is the example, like we are saying that healthier people have the better social relationship, so they have some correlation or the relationship. Similarly, we are saying also live longer, so better health also long live. Okay, if you have a better health, so there is a strong relationship that you will live long, so there is a relationship. But there is no correlation, there is no relationship, okay, between the social relationship and the long life. But we can say that if you have a good social relationship, then you may have a longer life. Okay, because the social relationship causing the better health, and it leads to the longer life. That is basically, you can say, in order to causing something else. Let's take some more example. Similarly, we can say that traffic jam can cause the bad mood. Okay. Similarly, traffic jam can cause the tidiness, whereas bad mood and the tardiness has a correlation. If there is a high, more and more bad mood we have, there is more and more tidiness we have. Okay. Similarly, we can take another example, that is hot weather causes higher sales in the ice cream. Okay. Similarly, hot weather can be higher sale in sunburn creams. Okay, but there is a relationship. As the sale of ice cream increases, we can say that the sunburn cream is also increasing due to the hot weather. So there is a relationship. Okay. Similarly, over here and over here. So I hope you have clear regarding what is the difference between the correlation and the causation. Now, the question is, under what circumstances we can pick what kind of the correlation technique we can apply. Okay. So as we know that the correlation is basically quantifying the relationship between the two variables. If the relationship between the two variables are the quantitative variables, okay, like whether we want to going to apply the parametric correlation coefficient technique while we are quantifying the relationship between the two variables, or the non-parametric technique, or the partial correlation coefficient. So let's first discuss the parametric technique. Okay, when we are saying the parametric correlation coefficient, which mean that out of the two variables, at least one of the variable must be quantitative variable, okay, and it should be follow the normal distribution. Okay, then the data must follow the normal distribution. So there is a two main condition. One is that it should be quantitative and it should be follow normal distribution. So in order to apply the Pearson product movement correlation coefficient, which we have calculated using Excel earlier, so for that both the variable must be the quantitative variable, as well as the both the variables must follow the normal distribution, mean the data must follow the normal distribution. Then you can apply the Pearson product movement correlation coefficient. So there is other two techniques as well in the parametric correlation coefficient. One is biserial correlation, another is called as a point biserial, because both of them are depending upon the Pearson correlation coefficient. So for that, one of that variable must be a quantitative variable and it must be follow the normal distribution. But the other variable, because we are going to apply biserial or a point biserial, so other variable must have the two category. Okay, that's why that particular variable is called as dichotomous variable. Okay. So now the question is, under what circumstances we can apply point biserial correlation, or under what condition we can apply a biserial correlation coefficient. Okay. So point-biserial correlation coefficient is actually the Pearson correlation coefficient mathematically. Okay, but we will apply the point-biserial correlation under the circumstances when one of the variable is a dichotomous variable, and it's a true dichotomous variable, or you can say it's a discrete or true dichotomous variable. True mean like such as gender. So it should be a true, whether it should be a male or a female, a boy or a girl. Okay, so it's a true dichotomous variables exam. Whereas biserial correlation can be applied when one of the variable is artificially dichotomous. Okay, artificially dichotomous means we are made that continuous variable in a dichotomous form, such as you can say the marks. Okay, for example, we have a variable that is called as marks, as well as the anxiety level. Okay, and students has the marks 80 marks, okay, 70, 75, 30, 31. Okay, so how we can make the dichotomous variable? We can say that higher than 30 is pass, okay, and less than or equal to 30 would be the fail student. So now we are forcing or artificially making the variable dichotomous type, okay, in a binary form. So in such case, we should apply the biserial correlation coefficient. So I hope you got the idea under what circumstances we can apply the Pearson correlation coefficient and under what circumstances we can apply the point biserial and then the biserial. Now let's say if the variables are the quantitative variables, or even if it is on a ordinal scale type of variable, mean the data do not follow the normal distribution, then we can apply the Pearson rank correlation, or either we can apply the Kendall's correlation coefficient. So usually it is recommended that if the data set is small, then you can go for the Kendall's correlation coefficient. Otherwise, you can also apply the Pearson correlation coefficient. And the third option we have, if the data do not follow the normal distribution, we can adopt the bootstrapping. So what is bootstrapping is basically it is a with replacement sampling. Okay, like for example, I am saying that the sample we have taken is, let's say, from the 5 different participants. Okay, the participant number 1, he has the marks 80. Or let's say I am applying the bootstrapping on a variable marks. The second participant has the marks 75, the third participant having the marks 90, the fourth participant having the marks 65, and the fifth one is 60. Now I want to generate samples, mean I want to apply the bootstrapping. And what the bootstrapping do is it will generate with replacement sampling. Okay, like if I want to generate based on these 5 respondent more 5 samples, so it will do that with a replacement. Okay, so out of these marks he will with replacement pick the 5 numbers more. Okay, like it could be this one again, the second participant is also 75. Okay, the third participant may be 80, 65, okay, maybe 75. Then again we are drawing a with replacement, let's say 75, again 80, the second student got 80 and 90 and so on. So you can generate as many number of samples as possible, it should be with replacement. And based on this data which we have increased from 5 to maybe 1000 or 10,000, so that data may start following the normal distribution. So then with the help of the bootstrapping we can apply the even non-parametric correlation coefficient, or even apply the parametric correlation coefficient. Okay, so this is basically all these techniques are the bivariate correlation coefficient. Now we come to the partial correlation coefficient, or we can say the partial correlation. So under what circumstances? So normally when we are representing the correlation, that is representing with small r, or we can say 1 2, that means correlation between x1 and x2. Okay, but when we are talking about the correlation coefficient of the point biserial, it is normally represented RP, and this is normally representing with RB. Similarly, the Spearman correlation coefficient, normally you can simply represent R, or sometimes people can represent with rho, or this is normally representing with tau. Okay, but you can also say that that is Kendall's correlation coefficient. Whereas the partial correlation coefficient is normally representing with 1 2 3, because over here in partial correlation coefficient we want to find out the relationship between the two variables by controlling the third one, mean we will assume that the third variable is constant, or you can say by removing the effect of the third variable we want to find out the relationship between the two variables, such as we have seen exam performance if there is a variable, and then we have the an anxiety, and then there is a revision. Okay, we want to find out the correlation between exam performance and then anxiety variable by removing the effect of the revision. Okay, so that is basically a controlled variable. So if we are doing this, so there is a mathematical way to calculate this one. So in that scenario we can apply the partial correlation coefficient. First of all, when we are saying the parametric correlation coefficient, and the first type of the parametric correlation coefficient is basically the Pearson product movement correlation coefficient, which we are representing through R, and we know that the correlation coefficient answer is lies always between -1 to +1. Okay, and how we can calculate this correlation coefficient? We can calculate using these formulas. So, any formula you can use out of these, either you can apply this particular formula or this or this or this, all are equal, so in order to find out the correlation coefficient. But before finding the value of the Pearson's correlation coefficient, the important thing which we need to test is that we can only apply this Pearson correlation coefficient if the data follow the non-normal distribution, mean it's a parametric, right? So both the variables, okay, both the variables must be the quantitative variable, or you can say the interval scale variable, right? And the second thing is they must follow the normal distribution. Then in that particular scenario we can apply the product movement Pearson correlation coefficient. So this particular value, this R value, is basically the descriptive value of the correlation, mean that is the relationship between the two quantitative variables. So similarly, we can also test whether the value of R is significant or not. So for that, we discussed that our H naught, mean our null hypothesis, should be that there is no relationship between the two variables, whereas alternative mean there is a relationship between the two variables, two quantitative variables. So this is the testing of hypothesis perspective. So this is called as two-tailed test, right? Similarly, we may have, that is the correlation coefficient is greater than 0, mean there is a relationship between more than or equal to 0, or alternative mean there is less than 0 relationship, mean negative relationship. So similarly, if we have less than or equal to, or H naught would become, that should be greater than. So this is called as one tail test, right? So it could be any condition, so you can test this one. Okay, if we talk about the non-parametric perspective, so the first is obviously the data must be the quantitative data, okay, of the both the variables, but it might be follow, they do not follow the normal distribution. They could follow any particular probability distribution, right? And the data might be follow exponential distribution or gamma distribution or any other kind of distribution. Then you can apply these non-parametric analysis or the correlation coefficient. But generally, people are saying that you can apply Spearman's rank correlation or Kendall's tau when your data having the ordinal scale type, right? But so how the now the question is how we can find out the Spearman's rank correlation. The formula is over here, because this method is purely basing on that we are actually ranking the data ascending order, okay, and then we are calculating the correlation between them. So similarly, the Kendall's coefficient is also a similar type of the Spearman's, mean it is also using the ranking perspective, but normally we prefer the Kendall's tau correlation coefficient when the data set is small, okay, when you do not have the large data set, okay, you have the small data set, but the ties between that those variables are large enough, okay, then we can apply the Kendall's tau test. And the third one is the third technique which we can apply in the non-parametric is the bootstrapping. So we have already discussed in the previous lecture, like what is, or you can say in the part one, what is a bootstrapping. So we will also discuss in this lecture as well quickly what is the bootstrapping and how we can apply using R. Okay, so for that I'm using the same data set which we have used in the part one, which is a exam and anxiety data. So in the column A, we have the code, or you can say the respondents, respondent 1, respondent 2. And this revise is basically indicating the total hours spent for revising the exam, or you can say revising the syllabus. And then the C is basically the exam marks in percentage. The D column, which is the anxiety, which is basically the anxiety score. Okay, and then we have a gender variable. Now using R we want to analyze it. So if we are want to analyze between any two quantitative variables, such as we are going to use exam variable, basically it's exam performance, an anxiety variable, and the revision time, which is in hours, okay, So what we can do if we want to perform the correlation? So the first thing is we can apply the graphical analysis, which is a scatter plot, and then we can apply the correlation. So let me show you in a R, and then we will come to this graphs interpretation. So for that, first of all, I need to load the data in R. So there are multiple ways to load the data. So the one of that is that I can use read.csv, which means I have the data set in a CSV format, and file.choose and header is equal to true. So file.choose the function, it will pop up a menu and allow me to pick a particular CSV file. And header is equal to true mean the first row of the data having the name of the columns. So if I run it, okay, so as I have told you, it will pop up the menu and you can see that here we have the CSV, that is a comma separated value file. I can pick it and open it. So now this data set is stored in the exam data, you can say variable. But if your data is in .dat format or in a text format, we can use this particular command. Okay, so either I can use file.choose or either I can use if your file is available in the same folder where you have created the R project. Okay, so you can also use this particular command. Okay, only read.dlme. Okay, and then name of the data file with the data type and header is equal to true. So this will also do the same thing. So if I run it, so now the data is in this particular variable, which is exam data. So with the help of this function, I can see the name of the columns, or you can say name of the variable. So this is a first column name, second, third, fourth, or fifth, or you can say name of the variables. If I want to see the data set, I can use view function, and remember that R is a case sensitive statistical programming language where V should be the capital. So if I run over here, so now I can see the data set. Okay, so this is the first, second, third variables, right? Now, in order to apply the scatter plot, what I am going to use is I am going to use the ggplot tool. Okay, so first of all, whenever we are going to use a particular package from the R, so first we need to install it. So from the package, okay, you can check whether you have the ggplot2 or not installed. So I have already installed it. Okay, so you can just click it, or either you can simply by calling, you can write on library ggplot2. So if you do not have this package, you can click on the install, you can write ggplot2. Okay, make sure your computer is connected with the internet, and then you can install it. So once you install it, either you can write library ggplot in order to call this particular package, because we are going to use different functions that are available in this particular package, or either I can simply click over here, so it will automatically call this particular package. So from this particular package, what I am going to do is I am going to apply the scatter plot. Okay, and I'm interested in finding the relationship between the exam anxiety and the exam performance in terms of marks. Okay, so for that, what I need to do is I am saying that ggplot, okay, that is the name of the function, and I want to draw a plot of exam data. Okay, that is basically the data frame which we have already stored in this particular variable, and then I am saying that what kind of the variables I am calling, mean against what I am going to apply the plot. So that is basically the anxiety and the exam. Okay, and then I am saying scatter plus, which means this particular variable, which means this function is continue, because I need to tell what kind of graph I'm going to apply. So that's why I'm saying scatter plus. Okay, or either you can simply write plus over here and so on, you can do that. Okay, but right now, after making a frame, so now I am saying that scatter, that is the name of the variable, plus gum underscore point function, which is basically draw the scatter plot, and I am labeling x-axis and y-axis. So if I run this command and run this command, so I can see that from the plot section On the x-axis we have the exam anxiety, on a y-axis we have a exam performance. So let me interpret it, how we can interpret this particular graph. So I have also written here the commands which I have used in the R. So from this, first of all, we can see that the majority of the students suffered from the high level of an anxiety. Okay, so due to the exam pressure, we can conclude that majority of students do suffer in the high level of the anxiety. Very few have the less than 60 percentage of the anxiety level. Okay, and the second thing which we can find out that there is no outlier, which means all the data points are lying nearhood with each other. Okay, in the neighborhood of each other. So that's where there is no extreme point, such as maybe data point lie over here or over here from you can say away from the other data points. Okay, the next thing which we can see that the students with the low level of anxiety are almost always associated with the high exam mark score. Okay, so which we can see that if your anxiety level is low, okay, your exam performance is quite good. Okay, furthermore, and having the high anxiety, so there is a lot of variability in terms of the exam performance. If there is a high anxiety level, so we can see that there is a lot of variation in the results, right? Furthermore, we can say that there is a no such case we have found that having the low anxiety and having the low performance, there is no such data point. So which mean if there is an anxiety, it might be possible you perform maybe better or maybe low, but there is a lot of variation depending upon the student. Okay, furthermore, if I want to find out, so I have just incorporated two more elements. The same command will remain same. Now I am saying coloring with gender. So now I want to find out out of all these data points, because in the data set, one of the variable is a gender. We can see that whether male are doing something else in the anxiety or whether the female. So we can see that there is no such difference we found whether the gender is male or female. Okay, almost similar kind of performance they are performing. Okay, so no matter whether it's a male or female, if they have the anxiety level low, okay, their performance must be good. Okay, but if there is an anxiety level high, so their performance having lot of variation. Okay, no matter whether it's the gender is male or the female. Okay, now let me draw this gender plot with the help of this gender category. So as you can see that over here, and then we have also label it with color gender. Okay, so let me run this command, this one. So now you can see this one. Okay, now in order to apply the parametric correlation coefficient, which means the Pearson's correlation coefficient, so we have to check the normality of the data. So how we can do that? So there is a different way to check the normality. Either we can draw the QQ plot, either we can, which is quantile plot, either we can use histogram or the descriptive statistics, and the most importantly, either we can apply the test for normality. And there are multiple type of tests. So let's check one by one with the help of these, whether the data follow the normal distribution or not. Okay, so first of all, I'm using the descriptive statistics. Okay, the thing which I am going to show. Okay, but let me show you in the you can say from the R. So first of all, we are going to draw a histogram of which variable, that is the exam anxiety. So what this function is going to do is, that is basically for, in order to draw a histogram, we should use hist, then the name of the variable in which we have stored the data, which is basically the exam data, and with the help of dollar sign we can access the particular column. So let me show you. If I press dollar, we can see that the list of all the variables in the exam data. Okay, and then I'm going to store this histogram into this particular variable. So if I run it, I can see the histogram. So from this histogram, we can easily see that this do not follow a normal distribution. Okay, so if I run this particular variable, you can also check the counts. Okay, you can also check the breaks, that is 0 to 10 class, then 10 to 20 and so on. You can also check the counts and then the probabilities, okay, the midpoints of each class. Okay, so similarly, let me draw a histogram of the second variable, which is the exam performance. If I run this, so we can also see that it might be normal, but I'm not sure because histogram is a descriptive, but it might be possible it's a normal. So we are sure from the anxiety, from the histogram of the anxiety, that it didn't follow the normal distribution, but it seems might be possible. But let me apply the QQ plot of the exam anxiety perspective on the variable of the exam anxiety. So for that, we can use this particular function, which is a Q plot. Sample is equal to an exam anxiety. So if I click over here, so I can see the exam anxiety graph. Okay, sorry, the QQ plot graph. So if this dotted line is straight, then we will say that the data follow the normal distribution. But right now it is not a straight line. So that's why this data do not follow the normal distribution. So let me draw for the second variable. So in a second variable, it might be possible, as we have seen from the histogram, might be possible it follow a normal distribution because it is look like approximately a straight line. So now let's try some descriptive analysis. So if I run this describe function, so which is available in this particular package. So again, in order to use this particular function, we need to install this package. So I have already installed this particular package. So now I need to call it. So I will run it and then describe. So from here we can see that the value of the skewness is negative 0.36. So as we know that if the value of the skewness is 0, then we will say the data follow the normal distribution, which doesn't look like. Similarly, if the data is a normal distribution, we can also that the mean value and the median value must be equal. Okay. So from here, we cannot say the data follow the normal distribution. So another way is I can use this particular package, and in this particular package, there is a function called stat.des, which means describing. Okay, and we want to check whether the data follow the normal distribution or norm. So that's why I'm writing norm is equal to true. Norm mean normal distribution. Okay, so if I run this, so the advantage of this function is we can also apply the Shapiro-Wilk test, which is checking the normality of the data. So how we can do that? We can see that if the p-value of the Shapiro-Wilk test is greater than 5%. So how we can check that? That is basically that is when we are saying the data follow the normal distribution in terms of the testing of hypothesis. Over there we can write down H, the data follow normal distribution. Okay, whereas H1 would be the data do not follow the normal distribution. So what's the rule is, if the p-value, okay, whether you are going to apply Shapiro-Wilk or any other normality test such as Anderson-Darling test, okay, so if the p-value is greater than your pre-decided alpha, such as 0.01, which means 1% or a 5%, so if the p-value is greater than this one, we will say except H naught. Except H naught means that data do follow the normal distribution. If the p-value is less than alpha, then we will say data do not follow the normal distribution. So as we can see that from this particular command, okay, what we are getting is that is basically we are finding the normality of the data of the two variables, okay, with the help of this particular command. How we are using it? We are calling the exam data, that is a variable in which we have stored, and we are calling two variables. Okay, so we haven't mentioned the row, we said comma and the column. So that means all the values in these columns. Okay, and we are checking the normality. So for the exam anxiety, if we check the p-value, okay, from the Shapiro-Wilk test, which is the test statistic value, Because this p-value is less than alpha, we will say reject h naught. That means data do not follow the normal distribution of the anxiety variable. Similarly, if we check from the exam performance, because the p-value is again less than alpha value, which is either you are using 1% or a 5%, okay, the data do not follow the normal distribution. So theoretically speaking, we cannot apply the correlation coefficient on these two data sets. We have to use some non-parametric. But for the just practice purpose, we will find out the correlation coefficient between these two variables using the Pearson. But practically, you cannot apply the Pearson correlation coefficient between exam and anxiety because data do not follow the normal distribution. So we have to select one of the non-parametric method. So you can also get these values with the help of this command, which is a Sphero test. Okay, that is a Sphero-Wilk normality test. You can check that if I am calculating the running this command with the help of exam anxiety, mean that is a second variable. So this is a p-value, this is a test statistic value, which is the same these two values. Okay. Similarly, for exam anxiety perspective, these are the p-value and the Sphero-Wilk test value, which is we are saying that this one. So let me run these two commands in R. Okay, how we can do that? So first of all, we want to find out the descriptive analysis of more than one variable. So we can do that. Describe exam data, that is a variable in which we have stored the data, and we are accessing the two columns of the anxiety name and the exam. So if I run this one, so I can see that in anxieties variables descriptive analysis as well as exams variables descriptive analysis. Okay, the next one is that is if I run this particular command, we can see that this is showing us the Sphero-Wilk test as well as the descriptive analysis as well as the confidence value. But from the Sphero-Wilk test, we can easily say that the data do not follow the normal distribution. One more thing, as you can see that this is a scientific notation. Okay, this is a decimal notation. If you want to see this decimal notation over here, then you can use this particular command, which is option typing is equal to 99. Okay, if I do this and run this particular command, and now again if I run this one, now you can see that it is showing me in a decimal places instead of the scientific notation. Or either I can apply the Sphero.test, that is the name of the function to check the normality of the data, and then exam data $, the name of the variable against which you want to apply the Sphero-Wilk test. Similarly, for the exam anxiety, from both the tests, as we have concluded earlier, that the data do not follow the normal distribution. So basically, for exam anxiety as well as exam performance, if we want to find out the correlation between these two variables, we cannot apply the Pearson's correlation coefficient. We have to pick among the one of these three methods, either Sphero rank or a Kendall's or a bootstrapping. But for just practice purpose, currently what I am going to do is I will apply the correlation, Pearson correlation against these two variables. So for this, I'm using a function called COR, which is a correlation. Okay, and then the first variable and then the second variable, and then I am mentioning the method whether I want to find out the Pearson correlation coefficient, whether I want to apply the Kendall's, so then I need to write Kendall, and then whether I want to apply the Spearman's. Okay, so right now I am applying the Pearson's correlation. So let me run this command. Okay, so what I am getting, I am getting negative 0.4409. So how we can interpret it, that from here that they have the negative relationship, okay, between the an exam performance as well as the anxiety variable. So as the anxiety levels start increasing, the performance having the negative impact, okay, it will start decreasing, which we have already seen from the scatter plot. As well as the exam anxiety increases, the exam performance trends decreasing, so it's a negative relationship. But now we need to see that whether this relationship is significant or not. So for that we need to test it. Okay, so before running this coefficient of determination, let me run to apply the test. So how we can apply? So for that we have a command called cor.test. Okay, and then the name of the two variables against which we are going to apply, and then what kind of alternative you want to apply, whether it is not equal, okay, whether it is less than, or whether it's greater than. Because right now I am using less than. The method is Pearson. The confidence level I want to use 99, which means the alpha is 1%. So if I run this command, okay, so from here, this is the value of the correlation, this is the value of p value. So as we have already discussed, because this p value is less than alpha, which means not the greater than alpha. And what is the alpha? Which is 0.01, because we have considered the confidence level is 99%. So that means the alpha is the 1%. So this p value is not less than alpha. So that's why we can conclude that the data do not have any relationship between these two variables. Okay, so as you can see that for using this particular function, you can, if you want to use the two tail test, then you need to use two-sided or less than or a greater than. So for the method, if you want to apply the Pearson, write on Pearson. If you want to apply the Kendall's coefficient, then you can apply Kendall or a Spearman. So right now I have applied the Pearson correlation coefficient, right? Similarly, I can also find out the uh, coefficient of determination. So coefficient of determination is what? That is basically the square of correlation coefficient. Okay, let me run this particular command. Okay, this is correlation. Okay, basically it is right now representing in terms of all three variables between exam performance, exam anxiety, as well as the revision. So this is indicating the value of the correlation coefficient value between exam anxiety and exam performance. And similarly, this is revision between exam performance. This is between exam anxiety and revision. So we can see that exam anxiety and exam performance, they have the negative relationship. Revision and exam performance having the positive relationship, whereas anxiety and revision having the negative relationship. Okay, so this should be 1, as we can see that, and obviously these value would be the same like the upper one. And over here, this is the coefficient of determination, which is basically the square of this one. So what's the coefficient of determination? The coefficient of determination is always the square of the correlation, okay, which is basically indicating the overall variation, how much variation the one variable can explain in the others. Okay, so that is basically indicating that the exam anxiety can explain 19% variation in the exam performance. Okay, similarly, the 15 or almost 16% variation can explain of the revision variable in the exam performance, or you can say the contribution for this particular variable. So similarly, we can also use another you can say package, which is basically a graphical user interface package, that is basically R commander. So so for that, what we need to do is, again, we need to call that package. Okay, let me call. So if I run this particular command, okay, now right now it is calling that particular package. There is another window which is basically the R commander window. So for that, first of all, we need to access the data. So for that, I will go to data, import dataset, and then I need to tell what kind of data file you have. So right now I have the same dataset in the Excel format. If I run over here, okay, and simply press OK, and then I can pick this basically the Excel file over here. This is an exam anxiety data file. So if I run this one, if I click the view tab, so this is basically the exam data we have imported. Okay, so in order to apply the correlation, what I need to do is I need to go to stats. Then I can either apply the correlation matrix or the correlation test. So you can check what's the difference. So if I, let me show from the PPT. Okay, so that is first of all, I'm checking the normality. I will come later. okay, with the help of R command. So either we can pick the correlation test, okay, or either we can pick the correlation matrix. If I select correlation test, so then we have get this particular menu, and from this we can pick any two variables like anxiety as well as exam. So I can select what kind of the correlation you want to apply, the Pearson product movement correlation coefficient or the Spearman or Kendall's, okay, whether the test is two one sided, okay, you can pick your choice from this one, and then simply press OK, you will get the result. Similarly, if you are going to pick the matrix, so from that you can also apply the partial correlation coefficient, which we will discuss later. But over here in the matrix, there is no option for the Kendall's, so you can only apply Pearson or the rank. Okay, so right now we want to apply the Pearson correlation coefficient, so it's up to you. Either you can use this one command or this one command, so you will get the results. Okay, so let me show you through R commander. So what I am going to do is stats. First of all, I'm going to matrix, anxiety, and the exam variable I am selecting with the help of control button. Okay, so first I will select the exam anxiety variable, then pressing control, then I will click exam Pearson. Okay, and then I want to get the pairwise p-values. So that is basically I also want to apply the testing of hypothesis. If I press OK, so you can see that this is basically the answer between the correlation coefficient value, which is R, and it is also telling us how many observation, I mean the number of data points. This is also indicating the p-value. Okay, so this p-value is less than 1%, which means this is a significant relationship, which means the H naught is rejected because over here the H naught says there is no relationship, whereas H1 says there is a relationship. So as we can see that this particular p-value is less than your alpha, which is either you can use 1% or a 5%. So this is less than 1%. So that means we will say there is a significant relationship between the exam anxiety and the exam performance, and they have the negative relationship. As the anxiety levels start increasing, the exam performance will be decreased. Okay, so it is also showing us the adjusted p-value. So whichever you want to use, whether you want to use this particular value or this method, so both, with the help of both, you are getting the same result. Similarly, you can also use this particular command as well in order to find out the Pearson correlation coefficient with the help of R commander. Okay, so earlier as I told you that with the help of core or core test, which we have already applied in order to get the correlation coefficient, there is another command you can use in order to find out the correlation coefficient, which is RCORR. But for this you need to use this particular package, which means you need to install this package and then call this package in order to apply this function. So over here I am showing you the difference between these functions. If you are going to apply this function, you can get the Pearson correlation coefficient answers, Spearman's, Kendall's, but you wouldn't be able to apply the test statistic. Okay, over here test means you would not be able to get the p-value. Okay, where over here you can apply all three, as well as you can also get the p-values, as well as you will be able to get the confidence interval. Whereas if you are going to use this particular function, so you would be able to use Pearson as well as Spearman's, but you cannot apply Kendall's coefficient, as well as you will get the p-value. So we have already discussed how we can interpret it. Let me quickly discuss again. So if the p-value, as we have told you, if I am going to apply, because this is less than, which means I am saying that the H naught is greater than or equal to 0, or alternative is less than 0. So okay, because this p-value is less than how much confidence level we have used. We have used 99%. The alpha value is 0.01. Because this p-value is less than this one, we will say reject H naught. Okay, so if we are rejecting H naught, so that means there is a negative relationship between these two variables. Which two variables? That is exam performance as well as the anxiety level, right? And the value of the correlation coefficient is this. Okay, now as we have discussed earlier, if the data do not follow the normal distribution, or we haven't measured it in an interval scale, we have measured in an interval scale, sorry, in an ordinal scale, then we have to apply the non-parametric correlation. So for that, either we can apply Spearman's correlation coefficient or Kendall's or bootstrapping. Okay, so for that, what I'm going to use is I'm going to use a data set that is biggest liar data, that is basically having the two columns right now. One is the creativity, another is the position. So what this data says that I have basically want to test the theory that the more creative people will be able to create the you can say false story. They can make the false stories. So what I have get is I have get the 68% contestants data, and then I have also get their position, so their creativity and their position. So which mean more you have created the false story, you will get the higher position. Okay, so this creativity is basically you can say the marks, right? So because the position is an ordinal scale data and we want to find out the relationship between the contestant's position and the creativity, although creativity we can say that in trouble, but this is ordinal, so we are going with the non-parametric analysis. So for that we will going to apply the Spearman's correlation as well as Kendall's coefficient. Okay, so first of all, with the help of this command, which is I'm using the R, okay, I'm accessing the data. I can view this data set. Okay, then I am applying this command in order to find out the correlation. Okay, the H1, which means I'm saying that H naught rho is greater than or equal to 0, whereas alternative is rho is less than 0. So that means over here I am saying that they have the positive relationship or a no relationship, whereas over here we are saying that there is a negative relationship between these two variables. So once I have run this by writing the Spearman's, I am getting these values. So rho is negative, this one. So from this we can easily say that so they have the negative relationship, as well as by default the alpha is 5%, this p value is less than, so we can easily conclude that there is a significant relationship between the creativity score and the position held in the world's biggest liar competition. So they have the negative relationship, right? So similarly, as you we have collected the data and we have seen that so the relationship is negative, mean that there is a creativity is high, mean as the creativity increased the position decreased. Okay, so which means the lower number that you did in the computation, which mean if the position is 1, so that means the actual number is decreasing. Okay, but the creativity is increasing, because if your marks is high, okay, you have the higher marks, that means you have the higher position. Higher position mean 1, so that's why we are saying in terms of numbers it is decreasing. So that's why the interpretation will be as the creativity increases, position decreasing from 4 to 3, 3 to 2, 2 to 1. Okay, so which means we can say that as the creativity increases, so did the success in the competition is also increases. Okay, furthermore, if you want to apply the candles, so same kind of result we are getting. So they have the strong correlation between the creativity and the position. Okay, and we can also see that they have the negative relationship. As the creativity score start increasing, the position is decreasing. The position decreasing means it become from 4 to 3, 3 to 2, 2 to 1. Okay, so I believe it's clear how you can interpret these results, whether you are going to apply the Spearman's or a Spearman's test or a Kendall's correlation coefficient. Okay, now let me discuss regarding the bootstrapping. As we have discussed earlier that if your data do not follow the normal distribution, so the third technique you can apply, that is a bootstrapping. And what is a bootstrapping is basically a statistical procedure to resample the data set. Okay, so which means you can create with replacement sampling that data again and again and as many times as you want. Okay. So for that in R, what we need to do is we need a library called boot. So that means first of all we need to install this and then call it. And then what I am saying that I'm using this particular function. So what this function is going to do is that is function, then the name of the variable in which we have stored the data. So that is a layer data. Okay, that is basically the layer data set. Okay, which is we have stored in this particular variable. And then I is basically indicating a particular bootstrap sample, because if you want to apply the bootstrapping to generate 2000 or a 10,000 sample. Okay, so for every particular sample we are representing through I. So sample number 1, sample number 2, sample number 3, and so on. So this I is basically representing each bootstrap sample. Okay, and then we are saying find the correlation against every sample, okay, of the variable position and the creativity, and the method you need to apply, that is the Kendall's coefficient, because the data is non-normal. Okay, so the method we are applying, that is Kendall. So either you can apply Pearson or Spearman, it's up to you. And then I'm storing this function in the boot top, and then we need to tell how many time I want to bootstrap the sample. Okay, so for that I am again defining a variable in which I'm calling a function that is a boot. Okay, then the name of the variable in which we have the data, and then the name of the variable in which we have applied that function, which mean against which two variables we want to find out the correlation and using what method. And then we are indicating the number of bootstrap sample. Okay, and then I am running this particular command as well as I am running the confidence intervals. So let me run this command first and then we will analyze the results. So with the help of this command, we can call the data set. Okay, that is basically the biggest layer data. Okay, I can view this data set. Okay, right now I'm using the first two columns. Okay, either we can use simple R commands. Now I want to apply the bootstrap. So library boot. So I have already installed it. Then I am calling this function, run this, and run this. So I'm getting these results. Okay, so how we can interpret this one? So from this, first of all, we can see that this is basically the answer of the Kendall's correlation coefficient, which we have calculated earlier as well. Okay, and furthermore, we can see that there is a very small standard error. Okay, so from the bootstrap, so there is a very small standard error. So that means we can rely on these results, as well as in order to check whether this relationship is significant or not, what we can do is we can use these confidence interval with the help of norm, basic, percentile, and DCA. If any of this confidence interval containing the value of 0, then against that particular confidence interval we can say that based on that particular confidence interval there is no relationship between the two variables. So as we can see that whether we can use this particular confidence interval, whether we can use this or this or this, so none of the confidence interval containing the 0 value, because when we are applying the testing of hypothesis, we say that rho is equal to 0 and alternative mean rho is not equal to 0. So this 0 mean there is no relationship, because none of this confidence interval containing the 0. So from the bootstrapping, we can conclude that there is a significant relationship between the creativity score and the position held. So as the creativity score start increasing, you will get the your position is decreasing. Position decreasing mean you are getting basically the higher position in terms of position number 1, 2, 3, right? I hope it's clear how you can perform the correlation analysis in R, the parametric, especially the Pearson correlation coefficient, and how you can interpret it. Similarly, the non-parametric, which is Spearman's, Kendall's, and Bootstrapping. I'm going to talk about the biserial and the point biserial correlation coefficient using R, as well as the partial correlation, or you can say the part and partial correlation coefficient using R. So first of all, let's discuss what's the point biserial correlation and what's the biserial correlation. So as we know that when we are talking about the correlation, that means we are talking about to check the relationship between the two variables. So when we have seen the parametric correlation coefficient and the non-parametric, the key point over there is we can apply them the parametric correlation coefficient when both the quantitative variable having the follow the normal distribution, whereas the non-parametric we can apply when the data do not follow the normal distribution. Okay, whereas the point biserial correlation coefficient as well as the biserial correlation we can apply in such a situation when one of the variable is a continuous variable, whereas the other variable is binary, or which we can say the dichotomous. So now the question is how we can differentiate between the point biserial as well as the biserial that is based on the dichotomous variable's nature. If the dichotomous variable is a true dichotomous, means such as gender, okay, that is basically male and female, so that is a true dichotomous, there is only the two categories, right? Or we can say the type of the drug, if we have only two type of drugs, okay, then we can say that it is A or B. Then in such case we can apply the point biserial. Whereas if this dichotomous variable is not a true dichotomous, it's an artificial dichotomous, mean we have made a continuous variable in the form of dichotomous, such as we can say the marks of the student. So that is naturally it's a continuous variable, such as students having the marks of 30, 31, 29, 40, 45, 50. So if I say that less than 30, less than or equal to 30 would be considered as fail, and more than 30 would be considered as pass. So we have artificially made this variable in the form of the dichotomous. In such case, we should apply the biserial correlation. Okay. Similarly, I have given the example of you can say depression level. Okay. Usually we have measured it in a continuous, but we can classify whether it's a high depression level or a low depression level, right? So that's why in such cases we can apply the biserial as well as the point biserial correlation coefficients. Okay, so but the main point is if we talk about the point biserial correlation, that is actually based on, or you can say this is a special case of the product movement Pearson correlation coefficient. So for that, let's see what kind of the data we are going to use, and then we will discuss how we can implement them using R, as well as how we can interpret the results. So the data set is available in this data file, which is look like this way, where time is a continuous variable that is measured in weeks, basically that sorry, in hours. So that is basically the number of hours that the cat spent away from the home. Okay, similarly the second and the third variable is basically a categorical, or you can say that dichotomous variable, such as 0 1, right? Where the gender 1 is represented with male and the 0 represented with the female. And then record is basically the opposite of the gender, okay, where we have represented 0 with the male and 1 is a female. So why we have done this, we will show you, especially when we are going to apply the point biserial correlation coefficient. But right now we will use these two variables in order to calculate the point biserial, because we know that one of the variable is a continuous, whereas other variable is a true dichotomous variable. So for that, the research question is in which we are going to answer, that is there a relationship between the gender of a cat and how much time it spent away from the home? Okay, so we are going to answer this question. So this is a true dichotomous variable, whereas this is a continuous variable, so we can apply the point biserial correlation. So how we can do that in R? So let me open the R studio. So in order to apply this point biserial, first of all, I am going to access this dataset using this following command, where read.csv is going to read this data file, which is available in the same folder in which I have created this, you can say, RStudio project, where header true means the first row heading would be considered as the name of the variable, and then I am going to store that entire data frame into the variable called get data, and then I am running the correlation normal, the Pearson correlation. Okay, that is with the help of gender. So you can see that the answer is 0.37. Similarly, if I run it with the help of time and record, okay, the answer will be the same, but only the difference is between the sign. Okay, so let's discuss what's the meaning of this one. Like, as I have using the gender, I will get the answer of this correlation. If I'm using the record, the answer will this. Okay, the difference is, whereas in gender variable we have represented 1 with male, okay, and 0 with female, whereas in a record variable 1 is representing female and 0 is representing male. So if you remember, when we will talk about the Pearson correlation coefficient, we will say the correlation coefficient tell us about the direction and the strength of the relationship between the two variables. Whereas when we are talking about the point biserial, we should ignore the direction of the relationship, because it all depend on the dichotomous variables value, or you can say the coding, how you are coding that dichotomous variable, whether 1 is representing male or whether it's 0 representing male. Okay, so that's why we should ignore this sign, and we should only check whether this relationship, which is 0.37, is the significant relationship or not. Okay, that is only we are getting the strength between the two variables. So as we can see that the p value, okay, if we can see that, so as we know that h naught, that means there is no correlation, whereas the h1 there is a correlation between the two variables, and we are using right now two-sided correlation coefficient. We are testing that because this p value, okay, this p value is less than the alpha value, which is 95, which means the alpha would be 0.05 if our confidence interval is 95%. Because this p value is less than 5%, so we will say there is a significant relationship between the gender of the cat and the time spent away from the home. Okay, which means one of the gender is spending more time out of home compared to the other, right? So that means we, based on these p-value, we are saying that there is a significant relationship between the gender of the cat as well as the time spent away from the home. So if I square this correlation, as we know that the answer would be equal to the coefficient of determination. So how we can interpret this one over here? That would be interpreted as that's a cat's gender variable counts 14.3% of the variability in the time spent away from the home. Okay, so that would be the interpretation of the coefficient of determination, which is indicating how much variation one variable can explain in the other variable. Okay, so as we have seen that one of the variable is a gender, in which we want to check whether this variable has a relationship between the time spent away from the home. So this is a categorical variable, whereas this is a continuous variable. So that means in such situation we can also apply some other statistical techniques as well in order to answer the similar kind of answer. So what are those techniques we can apply in this particular situation? Independent sample t-test, as well as the linear regression analysis with the dummy variables. So which we will discuss in details in the coming videos of these lecture series of the multivariate analysis using R. So I hope you got the idea under what condition we will apply the point biserial, and how we can interpret these results. So now let's talk about regarding the biserial. Although the biserial correlation coefficient we are applying in such a scenario when one of the variable is a continuous whereas other variable is artificially a dichotomous variable. Okay, as I have given in the example of such as the marks of the student, and we convert them into pass or fail. Similarly, depression level, it's a continuous variable and we convert them into high and low. So we artificially convert the continuous variable into the dichotomous variable. So in such case, we can apply the biserial. But over here, only for the just practice purpose, I am applying on the same data set, that is the gender of a cat as well as the time span. I'm applying biserial. So remember that actually we can only apply the point biserial, but just for the practice purpose, we are doing this. So in order to calculate the biserial correlation coefficient, so I'm using a package that is called as polycore. Okay, so that is over here. So if I run this one, so first of all, if you do not have this package, you can go to install and then you can search this package. Okay, okay, that is over here. You can click install. So once it's installed, so you use this particular package library polycore, or you can use require polycore in order to call this particular library, and then you can run polyserial. Okay, that is the name of the variable, which is the cat data is the name of the variable in which we have the entire data set. With the help of this dollar sign, we can access a particular variable. Similarly, the second variable, and if I run this one, I can get the answer of the biserial correlation. Okay, so now similarly the interpretation will remain same as we have interpreted the point biserial. So let me calculate the r square. So what is the r square? That would be 0.2255. So again the interpretation remains same as we have discussed in the point biserial, that is cat gender count for 22.56 of the variability uh, is spent in the away from the home. Okay, that's the variability, that much the variability that the cat jetter can explain in the time spent away from the home. Okay, so now let me show under what condition, what kind of the correlation coefficient we can apply. So like we haven't discussed these one. Okay, but we have discussed if the one of the variable is ordinal and the other one is also ordinal, then we can choose one of them. Okay, either we can apply Spearman rank order correlation coefficient or the Kendall's coefficient. So both of them you can apply, but I have told you earlier that so Kendall's stock coefficient you can apply in such a scenario when you have a small data set or you have the high ranked data, that under that condition you can apply candles. Whereas if one of the variable is interval or the ratio scale variable, or you can say the continuous variable, whereas the other one is the nominal, then over there we should apply the biserial or a point biserial. But if the nominal scale, which is also known as the dichotomous variable, is the artificial dichotomous, then we can apply biserial. Whereas if it is a natural dichotomous, then we should apply the point biserial. If one of the variable is the interval or a ratio scale, whereas the other one is the ordinal, so again we can apply Spearman's or the Kendall's coefficient, right? Similarly, if both the variables are interval and ratio, then we can apply Pearson product movement correlation coefficient if the data follow the normal. If data do not follow the normal, then we can apply bootstrapping or even Spearman's or Kendall's coefficient as well, right? Okay, now let's talk about the last type of the correlation, which is the partial correlation or the part partial correlation. As we have discussed earlier, so we can apply the partial correlation or part partial correlation coefficient when we are interested to find out the relationship between the two variables by controlling the effect of the third variable. Okay, or you can say the effect of the third variable we should held constant. In such scenario, we can apply the partial correlation coefficient, right? So let me find out the correlation between using the same dataset, that is an anxiety and as well as the exam. whereas we will make the Rivian as a control variable. Okay, so let me first of all access the data set. But before that, in order to apply the partial correlation coefficient, we need a library called ggm. Okay, so I'm calling this library. I have already installed this package. So now I am calling a data set, that is the exam anxiety data which we have used earlier. And from this data set, I am accessing three columns, that is exam performance in anxiety and revise. Okay, and storing into a variable called exam data 2. Now, in order to apply the partial correlation, so the command is, that is pcor. And what's pcor do? First of all, you have to tell the two variables in which you want to find out the correlation, whereas the third variable is representing a control variable. So after the two variables, you can show them as much as control variable you want to represent. So right now we are interested to find out the correlation coefficient between the exam performance and anxiety by controlling the effect of the Rivian time. Okay, and comma, and then we have to tell in which variable this data set is available, that is for in exam data 2. So if I run this command, and again, so we are getting the partial correlation coefficient. So in order to find out the r square, so I am just taking the square of this one, as well as in order to perform the test. So how we can do that? We can use this particular command, where this pc is basically indicating the variable in which we have calculated the partial correlation. Okay, that is basically indicating the partial correlation coefficient value. Okay, whereas one is representing how many variable you have controlled. So we have only controlled one variable, and how many observation your data have, or you can say what is the sample size. So that is 103 data points we have in that data set. Okay, so where it come from 103, let me show you this view, and let me show you this data set. Okay, so if you can see from here, we have 103 numbers, right? So that's where the sample size is 103. So if I run this one, so we are getting this result. So let me interpret this one. So how we can interpret? So this is the partial correlation coefficient, and this is basically the coefficient of determination. So this, which is basically indicating that the exam performance account only 6% of the variation. Anxiety can count only 6% of the variation in the exam performance by controlling the effect of the Rivian time. So that is basically how you can interpret it. Okay. So similarly, the test statistics, because the p-value is less than the 5%, so we can say that this relationship between the exam anxiety and the exam performance is a significant relationship, right? So I hope it's clear regarding how we can perform the Pearson, as well as the non-parametric Spearman's, Kendall's, Bootstrapping, Biserial, Point-Biserial, and partial correlation coefficient. So how we can do that in R. So now let me discuss how we can report them in our research. So like the first example is that is basically from the exam performance data. So we are saying that the exam performance was significantly correlated with the exam anxiety variable, and we are representing the value of R, okay, in order to show the direction. Similarly, we are representing that the time spent revising revising the exam syllabus having this particular value, and we are saying the time spent revising was also correlated with the exam anxiety, and we also reporting the p values and showing them that all the p values are less than 1%. Okay, so this is how we can report it. Similarly, from the second data set, I am saying that the creativity was significantly related how well the people did in the world's biggest liar competition, and I'm reporting the value of the correlation as well as the p-value. Similarly, we have also done with the Kendall's coefficient. This is Spearman's, this is Kendall's correlation coefficient. So if you want to report in a tabular form, so how you can do that? So we have represented all three variables, and at the diagonal values is always equal to 1, and we are in telling them what is the correlation value between the exam performance and the exam anxiety. Okay, similarly, what is the correlation coefficient value between the exam performance and the revision time? Whereas these three stars are indicating that the p values are less than 1%. Okay, so if there is a 2 stars, so you can say that it is less than the 5%. Okay, so this is how you can represent this is 1%, and then this is less than 5%. So this is how you can tell them whether it's a significant relationship or not. So as there is a stars, so if there is no star, that means that though between those two variables there is no relationship. If there is a 1 star, so the p value is less than 5%, 2 star less than 1, and then zero point 0.1 less than 0.1% is, that is basically indicating that it is the significant relationship. So over here we are indicating the number of values, okay, or you can say the sample size. In order to draw the correlation matrix, or you can say to visualize the correlation matrix, so we need another package called as ggcorr plot. Okay, so first of all we are going to install it. So I have already installed it. Now I am calling this particular package. So in order to draw the correlation matrix, the dataset I am using, which is the built-in dataset, which is mtcar. So I am just calling that data. So you can check the dataset using mtcars. That is the name of the variable in which the entire dataset is available. So right now we are interested, first of all, to find out the correlation between all these variables. Okay, so how we can do that? We can use the function called cur, then the name of the variable in which we have the entire data set. Then using the round function, I am saying that show me the correlation from after the fraction point up to 1 digit. Okay, and then I am storing that correlation matrix in the variable called as CORR. Okay, and then we can see this is the correlation between all the variables. So CYL and MPG, so these two variables having the strong negative correlation. So similarly, WT and DISP display having the strong positive correlation. Now, in order to check whether these correlations are significant or not, so for that we need to find out the p values. So how we can do that? We can use the function of cor underscore pmat from this package. Okay, and then the name of the variable in which we have the entire data set. So if I run this, and then I am just checking the first 6. So if you want to check the entire p values matrix, so you can write on simple p dot mat. Okay, that is the name of the variable in which we have the p values matrix stored. Okay, so as you can see that over here we are saying that it is a strong negative relationship between CYL and MPG, and the p values is indicating because this p value is almost 0, which is less than 5%. So that means we can say that reject H naught. That means CYL and MPJ has the significant relationship. And what kind of significant relationship? They have the negative relationship. Okay, so by increasing the MPG, so there is a significant decrease in CYL. Okay, similarly we can see DISP as well as MPG having the significant relationship, and this is the correlation is saying that they have the negative relationship. Now the question is, if we want to visualize this correlation matrix instead of getting the numbers, so we want to visualize it. So for that we can call a function called ggcorr plot, and then the name of the variable in which we have a correlation matrix. So if I run it, so you can see that this is the correlation. We can visualize the correlation matrix. So over here, so darker the color is indicating the darker the higher the correlation. Okay, so as you can see that the red color is basically indicating the positive side. So lighter the red color, that means lower the correlation. Okay, whereas over 0 we have almost white color. whereas the negative correlation are represented through by default blue color. So the lighter the blue color is indicating the lighter the correlation between the variables. So over here we can see that it is a square uh, uh, symbol they have used to represent the correlation. So if you want to use the circle, so we can use a method called circle. So I am running the another command. So now instead of showing in a circle, it is showing a square. It is showing us the in circle. The next thing is, now if you want to make the hierarchical cluster, which means it is trying to get a cluster of the similar type of correlation. Instead of right now, we can see that it is quite in a scatter form. So after applying this HC order is equal to true, that is the hierarchical cluster is order is true. So that means the similar type of correlation is going to be near with each other. Okay, so that is I'm saying the outline of the color, so that means this circle's outline should be white. Okay, so if I run this one, so now you can see that they have reordered this graph. Okay, and the blue colors, most of the blue colors are having the same cluster over here, the red colors are having the clusters over here. Okay, so that is by doing the hierarchical cluster is true. Now, if you want to add the correlation values in these circles, so how we can do that? By simply adding a command label is equal to lab is equal to true. Okay, this is basically label is equal to true. The rest of the thing is same. So if I'm doing this, you can see that they have added the correlation coefficient values. Now, if I want to see that which one is the significant, which one is not significant, so you can add another object that is basically p dot mat is equal to p dot mat, which we have already calculated over here. Okay, so if I run over here, okay, so you can see that the cross, so these two variables do not have the significant correlation. You can also check from the p-value matrix as well. So this is also not a significant. So wherever you have seen the cross, so that means among those two variables there is no significant correlation between each other. Okay, now as we know that whenever we are drawing the correlation between the variables, so these two values like this one as well as that is wt against you can say that, so they have the symmetrical in nature, the correlation matrix. So what does this mean? That mean the draft and carb, as well as you can see that the draft and carb, this minus point one and this minus, this is the same value. So which means the upper triangle is equal to the lower triangle. So these are the same numbers as you can see over here and over here. So if I want to see only the lower or the upper correlation, so I can add the type lower, so it will show me the lower correlation matrix. So if I add over here upper, so I can see the upper correlation matrix. Okay, so the label is true, so which means I want to add the correlation values, as well as the label size is going to be 3, so that means I am mentioning the size of this correlation values. Okay, I'm also mentioning the colors. Okay, so these are the different colors, so that mean I am saying that the positive correlations, the negative correlation are showing with the greens, okay, with zeros, okay, this, or you can say the smaller correlation are much whiter. Okay, and then I am using the theme, so that is basically the graph's background theme, and the title of the graph is going to be Correlogram of the empty cast dataset. So if I run it, now you can see that, okay, so right now it is showing me the positive correlation with respect to the green color, the smaller correlation are with respect to the white colors. Okay, or you can say much whiter as the correlation start decreasing. Okay, if it is a negative correlation, I can see with the red color. Okay, so now with the help of this ggcor plot, we can draw the correlation matrix, or you can say correlogram of any data set. So in the last this particular graph, I didn't enter pp match, which means didn't mention which one is the significant. So you can add this one. So let me add this one as well. and then I can check that so which have the significant, which one is not a significant. As we can see that so these two variables, this one and this one, is not a significant correlation between each other. Similarly, AM as well as CARP do not have the significant relationship between each other. The rest of them has a significant relationship between each other. So I hope you got the idea how we can draw the correlation, the Correlogram, or you can see the correlation matrix using R. So thank you so much. See you in the next video.